Okay, so what we were talking about last time, of course, was what a context switch from heritage turkeys to multi-core caching. It's a little bit of an adjustment. But anyway, we talked about this kind of model where we have multiple processors. We talked about how systems aren't getting any faster, and so people's approach is changing. Instead of trying to run clocks faster and faster, we're running into physical limitations, so why not just plop a whole bunch of cores onto a system? And that reminds me, I actually have a circuit board about this large at home that I wanted to bring and show you all. It's a 64 processor system that I got to program when I was an undergraduate. Now you can get a little chip that's about an inch on a side and it's got 64 cores in it. And so it's just amazing how things are improving. But anyway, if we have these multiple independent caches of a shared resource, then clearly we need some kind of coherence mechanism between them. Otherwise, we start getting into all kinds of invalid circumstances as far as the state that CPU 1 sees with respect to what CPU 2 sees. So we have this cache coherence protocol. We started talking about MSI, which stands for modified, shared, and invalid. Those are the three states that this protocol has. And so caches can be, I should say caches. Cache lines can be in any one of these three states. So we had modified, which just means my processor has modified it. Nobody else should have a copy of it because I own it right now. Shared, so I have unmodified data, and other people can also have this unmodified data. So no processor has modified the data in that cache line. And then we have invalid, where you can have one cache that invalidates another cache's line if that processor wrote to that line or something like that. There's a few circumstances in which we need to do that. Also, if one cache has the line modified and another processor tries to perform a write to that line, you may need to load it in so that you can perform the modification. So you force the other cache to write the line back, invalidate it, and then this guy can load the line and modify it. So you have all these different interactions. I have for a long time wanted to incorporate some kind of exam problem or assignment problem involving simulating these protocols, but you can imagine the state machines are really tedious to get right, and so I don't know that it would necessarily be a learning experience or more of an experience just in frustration. But anyway, these help you to deal with cache coherence, and it allows you to make sure that everything is correct. But what people notice pretty quickly is that it's not very fast, and so there's a couple of optimizations that are widely utilized. You have MESI, which has modified, shared, and invalid, but we also introduce an exclusive state. And exclusive means I have this cache line loaded and no one else does. So if my processor then turns around and modifies it, then I know that I don't have to tell anybody else to invalidate the line. And if you imagine, this is going to happen very frequently because I'll have one program running on one processor and I'll have a different program running on another processor, and they're not going to be working with the same data because usually that is buggy behavior, not actually correct behavior. So you have the one program running, and it's interacting with data, so it can have a whole bunch of lines marked exclusive, and then if it modifies those lines, it can just move them straight into modified without having to talk to any other caches. So MESI gives you a big performance improvement. I get to stop communicating as much because I know I don't have to. Then there's MOSI, which has an owned state, and in this case, if I expect that things are going to be modified a lot in this particular cache line, I can move it into an owned state where now I actually serve data to other caches if need be. So you can see that MOSI is a little bit more complicated than MESI. So MOSI introduces more complexities here. So modified block in a cache can be marked as owned. I expect reads and writes to occur to this block, so the cache line is moved into owned. And now if other cores want to read it, then I just go ahead and give them my cache data. So now we have another bus between the various caches as opposed to between a processor's cache and main memory. And so ideally this improves the communication performance and also alleviates this whole issue of the write-back overhead. Okay. So that's the idea behind MOSI. AMD processors are sort of the most advanced as far as this these coherence protocols, you can see that they've combined both owned and exclusive. So they have Moesi, or I don't even know how to, I'm not even going to try to pronounce it. But anyway, yeah, I'm not going to try. So, and there's other ones as well, because you can actually have lines move between caches. So instead of saying, hey, I need to load this line, and I go and talk to main memory, if another cache already has it in the shared state, why not just suck it across? And so presumably you can engineer something that'll be a lot faster than going all the way out to main memory, something like that. You also have caches that can listen to what other caches are doing. We call this bus snooping or bus sniffing. And so the premise is that if I watch what the other caches are doing, what addresses are being accessed, and is it a read or a write, then I automatically know what to do in those situations. And of course, we also have the more entertainingly named bus snarfing, where if there are writes going against a particular cache line, then I'll go ahead and update my cache line with those writes so that I can have accurate data. So there's a lot of ways that these caches can work. Now, the one last thing to mention is that some caches, especially as you start getting into larger number of processors, all of the Intel, sort of x86 series processors use this bus snooping technique because they don't have that many cores all collaborating together. You may have pairs of cores that interact together that can have a shared cache and have independent caches that have to be maintained. And you may have like 6 or 8 cores on a processor, and that's about it. Okay. So bus snooping certainly works in those situations, but when you start getting up to larger number of processors, then you need to start having some sort of central directory that you can use to maintain cache line state. So there are a few details there. So yeah, Intel i7 uses MESIF. So, oh, I'm sorry. Yes, question. Should I go back a slide?
Yeah.
Okay.
First one's bus snarfing seems to be the straightforward way to keep track of when cores are writing to different places. Why isn't that used more?
Bus snarfing is just more complicated to lay out on the chip. Yeah, what you start running into, like why one idea, like there's some really good ideas, but they end up not being used because it just takes up a lot of silicon to lay out the circuits and everything like that. As we shrink things, these concepts become more and more common. But yeah, that's why you don't always see them, even though it seems like a really good idea. It's just like infeasible to implement at present. Cool. Any other questions? Sorry that I missed that. I'm usually really attentive. So MESIF is another protocol, and you can see that we have one more letter because we have a new state called forward. And again, we have this thing that caches can share lines with each other. And if you had a situation where a number of caches had the same cache line, and they all had it marked shared, now, when a new cache needed the line, well, you have to make a decision about which one of those caches should actually share the data. So one of them can be marked forward. And that way, that's the cache that actually passes along the information. So that sort of coordinates the information sharing between caches in these kinds of situations. You can imagine that the first cache that loads a particular block of memory marks it forward, and then every other cache that wants to read that cache line pulls it from the original cache and just marks it shared. And so the one cache is always going to be responsible for serving the line to other caches. Okay? I mean, the thing is, if you think about these things, and when you start seeing, okay, i7's got L1 caches, instruction and data caches, and those are pretty limited in the way that they're used, but they're isolated, so L1 data caches have to be coordinated across multiple processors. So we have a bus between L1 and L2, we have buses between everybody's L1. With all this crazy state machine stuff and being able to move data and stuff, and then we have L2, which is shared, but if you have 4 cores or 6 cores, then you may have multiple L2 caches that need to share data and be coherent. So then again, you have buses between them, and then buses to main memory. And so as you start adding these caches in here, you can see that the complexity grows really rapidly. And so that's why sometimes certain techniques aren't used. Okay, so let's say that we know how to solve this, because we do. MSI all by itself would certainly solve the problem, even though it's a little bit slow. So the question is, what new performance-related issues can we start running into with this cache coherence mechanism. And we'll start looking at some of these details. Let's say that we are a mediocre multi-threaded programmer, and we have a program that has some array of data, and we want to upgrade it from single-threaded implementation to a multi-threaded implementation. So that, because the thing is that if you have a program, and I hope none of you suffer under this perception, but if you have a single-threaded program and you run it on a 4-core or an 8-core machine, that doesn't automatically make it faster. We're not good enough to do that yet. One day we probably will be, and this is a problem that we've been working on for decades. I remember when I was an undergraduate attending talks where people were talking about how to solve these kinds of problems automatically. We're not there yet. But what I want to do is take this program and engineer it so that I can run it on multiple processors. That's what you generally have to do right now. You have to actually do the work yourself. So we have this program with 1,000 elements, and of course each element is 4 bytes. And let's say that we just run through them doing some operation. But each element of X is independent of all the other elements. So I don't know what we might be computing, but we have something where each element is independent. So we'll just have different threads updating different values. And the threads can run on different cores, and then we'll be fine. Everything will run faster. At least that's the idea. Again, we are slightly mediocre, so what we do is we say, one thread will get all the odd values. I don't know why anyone would decide to do this, but let's say that's what we decided. One thread gets all the odd values, and the other thread, or all the odd indexes, and the other thread gets the even indexes. Okay? So already we have a slight problem. And hopefully after last lecture and the lecture before that, you'll look at this and say, but Donnie, that's not a stride 1 reference pattern. I'm not using my caches as efficiently as I could be using them. And that would be a very good thing to say. Because it's not stride 1, it's stride 2. We'd like the threads to have a stride 1 reference pattern. So already we're sort of going in the wrong direction. So this is our multi-core processor that we're running on. We have cache coherence between these various caches. So what additional problem do we now have between these threads? Cache contention. What kind of contention do we have? You're on the right track.
Wouldn't they be bouncing back and forth for requests to be the correct number of X?
Why would that be? You're totally on the right track. Yeah.
Because cache page sizes aren't 1 byte or 1 long.
Yeah. So we have this thing. Let's assume that we're on Intel IA32, 64-byte cache lines, right? So we have 64-byte blocks. So that means that we can cram, 16 of those floats into each cache line? And so what we're going to have is one thread trying to do 8 of them, and the other thread trying to do 8 of them. And if they're running sort of at the same time and traversing the same indexes at the same time, we have this issue that both threads are going to be trying to write to this cache line. And the hardware will handle that perfectly fine because we have a coherence protocol. But the problem is we're requiring the coherence protocol to do a lot of work as our program does this rather inefficiently. But what's more unusual about it is that we really don't care about the values that the two threads are manipulating. So that's why we use this term false sharing. We have a situation where because of the way the cache lines are being used, the data is shared, and so the caches are keeping it in sync. But the program doesn't care. And so if we had no coherence at all, then our program would still be correct. But because we have the hardware assuming we need to keep these things coherent, which is a good assumption, it's a safe assumption, we have this situation where the overhead becomes very high. So like I say, the independent values reside in the same cache line, so we're doing a lot of work even though the program really doesn't care. Okay. So that's what false sharing is. And you pretty much nailed it when you were saying things are going to be moving back and forth really fast. Guess what we call it? Ping-ponging. Because you have a cache line ping-ponging back and forth between two caches, or perhaps even more if you have a really horrible situation. So caches have to coordinate operations on cache lines. So this is kind of what's going on. X3 equals something. So you load CPU1's cache, loads the whole cache line. And then thread 2 says, well, x4 equals something, and that causes CPU 1's cache to have to invalidate it because CPU 2 wants to write to it, and so forth. So you get this ping-ponging back and forth. This can lead to unbelievable slowdowns on programs that are multi-threaded. You take the single-threaded program and you rewrite it to be multi-threaded, and you think, aha, I will now be twice as fast or 3 times as fast. And of course, that's also not exactly the case because of Amdahl's law, which I'd love to talk about, but we don't until the OS class. But false sharing can cause that program to slow down by as much as 100 times, or I suppose you could even construct a bigger slowdown if you engineered it just correctly. Okay. But there are various research papers that talk about this issue of false sharing, and they see unbelievable slowdowns if you do not design your cache-friendly, multi-threaded programs very carefully. Okay, so that's the issue that you can run into. Now, like I say here, owned state protocols do help with this, because if I have an owned state, then maybe thread 1 loads that line first, and now it's marked owned, and thread 2, when it wants to write to it, well, now it has to shuffle the writes over to CPU 1's cache instead of going straight to main memory, which helps some. But maybe that's like 6 or 7 clocks instead of something that should be 3 clocks. So you still see a performance degradation with owned state protocols, but hey, it's way better than actually pushing it all the way out to main memory, or let's say even pushing it out to L2 where you might have a 15 or a 25 clock penalty for those kinds of things. So this is pretty big of an issue, and you really want to try to avoid it if you at all can. So a simple solution should be obvious. Make each thread keep its own data in its own units of cache lines. Even if you add a little bit of space to your system, you increase the space requirement, you're going to dramatically improve the performance. So our example program, what we could do that would make a whole lot more sense, even in the context simply of stride, is say, well, this thread's going to do the first half, and this thread's going to do the last half. I know, that's like brilliant, but that should be the approach that we should have from the very beginning. So we'll go ahead and do something like that. If you have a situation where you do have some kind of perhaps overlap of cache lines when you're designing your program, well, you can always pad things out. Pretty much every architecture will have specified somewhere how large the cache lines are, what size blocks they can hold. And like I said, when I give you assignment 5, there's a program that I'll give you that I wrote for funsies. I don't know why. But anyway, it'll actually print out the cache line size and so forth so that you can see exactly what your system has. And since you're all running Intel, it'll probably be 64 bytes. Okay, so yeah, data locality, not the only concern anymore. Now we have to actually start thinking about coherence protocols and how those interactions affect the way that our systems run. Okay, any questions? That is a really cool and important thing to think about. Now, another thing to consider, and somebody actually asked me about this after class, which was a really observant question, like, well, why don't we actually have these multiple processors share a cache? And that's what a lot of people have started thinking as far as processor design as well. Because we have this situation that cores aren't always doing similar tasks where their cache needs are actually the same. Let's say in our situation, like if I have a 2-core system that I'm using, I have 1 core running my MATLAB computation or my Mathematica computation, something like that. I'm clearly going to be hitting the cache hard. And CPU 2 is using the web browser. And most of the time the browser isn't doing anything because it's waiting for you to click on stuff or to scroll or for data to show up. So web browsers are actually bored most of the time. So in that situation, CPU 1 is the thing that actually needs a lot of cache, and CPU 2 really doesn't. Or at least it needs a lot less. If you're watching YouTube videos or something like that, it probably would need more cache. So we'd like to be able to dynamically shift our cache resources if we possibly can. And so this is why a lot of systems nowadays have shared caches between multiple processors. Okay. So like I say here, L1 and L2 are usually on processor. With the i-series, I'm really not sure anymore. So like the i7 has 3 levels of caching, and I don't know if all 3 are on processor or if L3 is off processor. Somebody may know that, but I certainly don't off the top of my head. Okay, but a lot of times this shared cache will also be on chip. And if you look at a processor die and you look at the picture of it, you'll see like big chunks of the silicon that are like, this is a cache, and that's all it is, so that we can make our systems run faster. Okay, so but the nice thing is when you have this shared cache, the cache lines will be allocated based on what reads and what writes are being performed. And so if you have one processor that's doing a lot of memory interaction, then it'll get most of the cache. And if you have both processors doing a lot of reading and writing, well, then they'll share it. And so having a shared cache works out really nicely when you have multiple processors that are doing possibly different things or the same thing. Now you have another really interesting benefit that sort of emerges from having a shared cache as well, because you have situations where both processors are actually running different threads in the same program. Or maybe they're running different programs that are communicating through shared memory or something like that. So we can actually pass information through L2 as opposed to having to go all the way out to main memory. So our L1 caches will still be generating misses from time to time, but we don't have to go all the way out to main memory. So we might have 25 clocks versus 100. I think I actually have numbers on this slide. Let me see if I do. Yeah, so CPU 1 writes a small chunk of data to memory. The blocks end up in its L1 cache. And then CPU 2 reads the same addresses because it's running other threads in the same process. And the blocks get shuffled through L2. They don't need to go through main memory because they're in L2 and it's a shared cache. And so when the reads and writes come in from the other processor, it'll just pull it from L2. Okay? So you see some interesting benefits here. There have been a few libraries that I've seen that actually take advantage of this thing, but they're actually kind of few and far between. So to me, this is a very interesting prospect for making high-speed communication between processors where you can actually utilize shared caches for this kind of thing. Okay, now you can still have false sharing, but you can see that if you have a shared cache that's not main memory, and let's assume that you also don't have any protocol with an O in it for owned state, then L2 sort of becomes your backstop as opposed to main memory. So that helps a lot too. Because when you have things ping-ponging back and forth between your L1 caches, because you designed your program badly, they'll still be able to shuffle through L2 as opposed to shuffling through DRAM. Okay? And so that can be really nice. That can be a big benefit. So like I say here, for a simple example, on the Core 2 processor, which I probably shouldn't talk about anymore because it's kind of really out of date. So L1 cache hit would be 3 cycles. Cache miss is 14 cycles. So ping-ponging through L2 is, like I say here, what, like 5 times slower than just accessing L1 and sticking to L1, but it's like, what, so L1 cache misses 14 cycles. Going all the way to main memory would be like 80 to 150 clocks. Way more expensive. You start seeing a huge performance slowdown if you're going all the way out to main memory. So L2 helps with this false sharing issue as well. Okay. Any questions? Okay, let's see what we have next. Yeah, so Core 2, this architecture, I already talked about it. L1 caches are independent. I already shared some of this information. MESI for L1 cache write coordination between processors. I don't think I have a slide for Core 7, which is too bad. So, or Core I series. So I'll have to add that next year. So multi-core and caching makes caching a whole lot more interesting. Thankfully, you don't have to think about it in CS24 very much. But one place, interestingly enough, that you have to think about it a lot is an operating system implementation. Because, hey, if you have multiple cores, you have this one annoying program that's running on all the cores from time to time, and that's the operating system kernel. And so you have to think about these kind of things. And so you can see that multi-core does make things pretty interesting because when you have these independent caches of a shared resource, you have to keep them coherent with each other. And that definitely increases the complexity both of how the cache is implemented and also how you interact with the cache. Okay, we talked about shared caches. I'm not really going to spend too much time talking about that. So yeah, you just have to think about this when you write multi-threaded programs that need to be high performance. You need to think about, well, is the information these programs are, or these threads are manipulating, is it actually independent, Or is the system going to think that it's shared because it's all on the same cache line and I'm going to start getting false sharing going on? Okay, so if there's no questions about caching, that is basically all we're going to talk about as far as caching is concerned. So, next thing. Now, we will talk about it again when we start talking about disks and main memory as a cache for disks. I don't want you to think that we're completely done with the concept of caching, but certainly as far as hardware caching, we're pretty much done. Now, the next thing that we're going to talk about is processors, and there's this annoying constraint that if you have one processor, you can run one thing at a time. If you have two processors, you can run two things at a time. But the thing is about programs is that they almost never use all of the computing resources of the system. There are a few kinds of programs that do. I imagine that, well, computer games are the easy ones because they try to push all of the hardware as far as they possibly can a lot of the time. If you have something like a first-person shooter, they're trying to get every clock out of every piece of hardware resources that you have. Same thing with high-performance servers. Obviously, they try to consume as many resources as possible to get their work done as fast as possible. But if you have like your text editor, or think about PowerPoint. Like PowerPoint is showing this slide and it's twiddling its thumbs waiting for me to push a button. That's all it's doing. And then I go and I'm like, ooh, blah, blah, blah. I talk and then I push the button and it's like, ooh, I get to do something. And it does it and now it just sits around waiting some more. This is the life of most programs. They sit around waiting. So that human beings are the slowest thing that programs have to wait on. But also if you're interacting with the network or you're interacting with a peripheral like a hard disk or a printer or something like that, you have long periods of just waiting. And the program doesn't have anything to do, so the processor would just be sitting idle if we had nothing else to do. Okay? So it's one of those interesting things. When we had older systems, like where each university would have one computer for the entire university and the terminals were lightweight and you would just interact with that one computer and you program it, and most of the time that computer is waiting for users to make up their minds about what to do. And so we need to find a way to utilize this shared resource in a more efficient way, a more economical way. And it's the same thing now. I have this processor, it's sitting around waiting. It really could be doing something else. So we'd like to be able to run multiple programs. Different programs is an obvious one. Multiple instances of the same program. If I'm building a large software project, I'd like to be able to run the compiler multiple times. I frequently have multiple browser windows open. And of course, Chrome has each browser window running in its own process to keep them isolated from each other. So we'd like to be able to run multiple programs at the same time. What is sort of the number one constraint we would like the computer to enforce or the operating system to enforce on our programs running at the same time? This is an easy one. And I've got my banking open in the web browser in one browser window, and I've got this piece of software I downloaded from some Eastern European website. I have no idea what it is, and I'm just going to run it and see what happens. What? I'm sorry?
Memory protection.
Yeah, memory protection. I'd like to have some way to prevent one program from messing up another program. Or let's say that I am doing something in one program, and in the other program I'm running my allocator, and it crashes, and it completely corrupts the heap as it goes down. Well, clearly I don't want that program misbehaving to screw up other programs. So we have this thing. We'd like to have some kind of barrier between different programs as they run. Programs shouldn't be able to access each other's data. And if a program decides to misbehave, it shouldn't take everybody else down. So we need some way of isolating programs from each other. So this is sort of what we'd like to be able to do with our, hey, let's run multiple programs at the same time. Let's say Firefox. How old is this slide? Does anybody here use Firefox anymore? Wow, a few.
Chrome broke recently with the video streaming.
Oh, okay, so Chrome is misbehaving right now. I get it. I have Firefox too, and sometimes I run Firefox. I actually have Firefox, Chrome, and Safari, and I picked one based on the specific need, but usually I'm using Chrome. But anyway, let's say that we have these two programs we want to run. Oh, and it's the same thing with GCC. It's like, well, Clang maybe, but let's talk about GCC. So we have Firefox and GCC that we're running, and the programs need to refer to their stacks and their heaps and their static state and all of that kind of stuff. So we have these things. How would we actually load both of these programs into our computer's address space all at once? How do we do this? Let's say that if you know what virtual memory is, that we don't have that yet. Well, one idea is, let's say that Firefox gets a certain range of addresses. What?
Sounds good.
Yeah, it sounds fantastic. What could possibly go wrong? And so it has that range of addresses, and then GCC is going to have another range of addresses. There really isn't a space between Firefox and GCC here. Yeah, not to scale. But anyway, let's say that we did this. The issue with this is that there's all kinds of problems with trying to design the system this way and trying to get it to work and actually being able to build isolation between our various programs as they execute. Okay? There's some really obvious issues. Let's even say that we have a way of protecting each program's address range from other programs. Let's say that we had a magical solution to that problem. It actually turns out that that solution is not very hard. Old systems solved this relatively quickly in like the late 50s and early 60s. So this problem has actually been solved before any of us in this room were alive. So anyway, we have these programs with their layouts like this. What if I want to run two versions of GCC? Too bad, right? I want to run two copies of GCC at the same time. I can't really do that. What if I have a program that wants to have more memory? Like GCC's memory utilization varies based on the side of the program it has to load. All those kinds of things. It has to think about that. Okay? So basically, this is a really over-constraining approach to solving this problem. We don't like it at all. So what we really would like to do is find a way to give each program this abstraction where it is the only program running on the computer system at that time. Okay? So that when that program is running, it thinks it's the only thing talking to the disk. It thinks it's the only thing in memory. It thinks it's the only thing accessing EAX and EBX and ECX and all of those things. So we'd like the program to think that. And then if there's another program running, we'd like it to also think that it's the only thing accessing all of that stuff. So that even if we had two programs that were using the exact same addresses in the program, we don't care. We have a way of solving that problem. In fact, this is actually a really nice thing, because if we can have the operating system specify the memory layout of the program and all programs follow it, program loading becomes simpler, debugging becomes simpler, because everybody's following the same set of rules. So suddenly, this kind of approach becomes extremely appealing. Okay, and so like I say here, the processor will somehow sort this out for us. We'll talk about how we actually do this efficiently. We're going to talk about an inefficient way of doing it for the next week or so, and then we'll start talking about more efficient ways of doing it. But yeah, programs have independent views of both the memory and the processor. That's basically what I'm saying here on this slide. In other words, what we're doing is we're virtualizing the processor. We're saying, hey, we've got this physical processor that actually runs every program, but each processor has a virtualized view of the processor where it thinks it has its own virtual processor. And then the next program thinks it has its own virtual processor, and so forth. So like I say here, we're introducing a level of abstraction. And we'll basically have to implement a mechanism that allows us to share this one physical processor, or two or four, or whatever you have, across multiple virtual processors. Okay? So that I can have 50 programs running at the same time, or 100, or 5, or whatever. I mean, anybody here that's using your computer right now, if you go in and open up a command prompt and type top, you'll see something on the top of the display saying, hey, you've got like 150 programs running it right now. Okay? No big deal. You have like probably 2 cores or 4 cores, something like that. Also, we will virtualize main memory so that we can give each program this perception that it is the only thing occupying memory right now. That will allow us to isolate each program's state from other programs, because if a program has the view that it is the only thing using memory, then that also implies that other programs' state isn't going to leak through, my state won't leak through into other programs, unless, of course, programs specifically agree to share memory resources. You can certainly create systems that do that. We'll talk about how to do that in like 3 weeks or so. Okay? But yeah, programs can use whatever memory layout they want, and it's not going to affect other programs. So this concept of virtualization is absolutely central in operating system design, implementation, and it's on your cell phone now. It is everywhere. It is completely ubiquitous. It's what makes computing fun. I don't know. That sounded good. Put that on a t-shirt. Okay, so this thing of a program running on a processor and all of the state that's necessary for doing that, it has a name. It's called a process. And I've used that term up here from time to time as we've gotten up to this point in the class, but I haven't really defined it. That's what a process is. It's a program with all of the state that's necessary during its execution. So this is the more formal definition, an instance of a program in execution. So you have the code, and then you have obviously the initial state, and then as it runs, it modifies its state, it modifies memory, it modifies its stack. All of that state, including the registers, all of that information, the flags, all of that is part of the process. And so the process is comprised of these two things, the program and all of its execution context. Those are the two things. And so, of course, you have this situation, the physical processor still can only run one program at a time, but what we can do is, if we have a way of capturing the context of a running program, we can sort of simulate, like we have multiple processors, by saving that context somewhere, and then we can move another program's context back onto the processor, and then resume its execution. So like I say here, when a process is running, it has exclusive access to the hardware until it's suspended and another process is given a turn. And then its context is moved off, another process's context is moved on, and it continues executing. So obviously, what state does this include? Well, I already have been talking about it a lot. So the context is going to contain all the general purpose registers. Okay, well that seems fine. We have these other things, the program counter, the stack pointer, the base pointer, and now we start saying, well, these things have addresses in them, so they reference the stack, they reference the heap. Oh, okay, so the stack and the heap are also part of the context of the program. So I need to make sure that I'm saving all of that kind of stuff. And like I say here, you need to make sure that you include the flags register, just in case you interrupt a program right in the middle of a comparison. Because, hey, it needs to jump next, but it didn't get around to it, so you saved the flag somewhere. So all of this stuff is part of the process's context. Okay? So we can save all of this stuff, and we'll look at specific ways of saving it. Assignment 6 and 7 have really unusual and pretty neat way of saving this stuff. Operating systems do it even cooler. So there's some really clever things that are done. And OSs actually do it very similarly to how Assignment 6 and 7 work. So when you see that, if it seems a little hokey, well then I guess OSs are hokey too. But that's just how people do it. It's really neat. Okay, so like I say here, we save all of the state into memory somewhere. And so we can switch the processor from running one process to another by performing this thing called a context switch. We change one process's context out and put another process's context in. Okay. Now, I want you to understand, context switches are not free. In fact, right now, we don't have any fancy memory virtualization, so they're unbelievably expensive. And initially, when computer systems were originally designed and operating systems were designed which had multitasking and they could have multiple programs running at the same time, in air quotes, context switches were incredibly expensive because of the way that it was done. So we had to design hardware to make it faster and make it better. But we'll get to that in a little bit. Like I say, there's two main ways to switch between processes. One is that you can have processes cooperate. What could go wrong? Okay, so every process does a little bit of work and then it voluntarily gives up the processor. I don't know if any of you have heard of a program yielding the processor. I mean, now Python has this notion of yielding a result, which is this weird generator abstraction. But that's not what I'm talking about. What I'm talking about is that a program yields, and what it's doing is saying to the operating system, hey, I want to voluntarily give up the processor. Somebody else do it now. Okay? And you can actually simulate this in Unix by sleeping for 0 seconds. That kind of says, hey, OS, I want to be rescheduled at a later date, so give somebody else a chance to run. The only issue with this, and it is a huge issue, is that if you have a program that either maliciously or accidentally decides that it is never going to yield the processor again, your system is now hung. This happened a lot back in the older days of like Windows 3.1, basically all the way up to before Windows 95, I think. We had cooperative multitasking in Windows. And I think Mac OS before OS 10 had cooperative multitasking. Did anybody use those OSs at all? Yeah, you all grew up in a world of competitive multitasking where you could not be hung this way. Okay. So anyway, the other alternative to cooperative multitasking is preemptive multitasking, where basically the operating system doesn't give programs a chance to be nice or be mean. It just interrupts them. Okay? Which is kind of nice because now programs have one less thing to think about. So in a way, it actually is a simpler abstraction for programs than cooperative multitasking because I don't have to think about other programs when I write mine. I can just think about myself. And the OS will forcibly interrupt programs when they're running and give other programs a chance to have the processor. Okay? So that's cooperative and preemptive multitasking. Now, one thing to mention about this cooperative multitasking, I don't spend a lot of time talking about it, but you'll see that there's a lot of situations where a program wants to do something and it's really slow. I want to open a file. Okay, 20 million clocks later, your file is open. Or I want to send data over the network. Okay, 15 million clocks later, your data has gone out on the network and you've gotten an acknowledge for it. All of this kind of stuff. In those situations, you can automatically switch to another process, even in the cooperative multitasking world. So it's really only when you have a process that's just sitting and doing computations that it needs to think about yielding. Most of the time, the OS that does cooperative multitasking can just interrupt the program anytime it's going to do something really slow. So it's not as impactful as you might think, but it is still something that you have to think about. Okay, any questions about that? Let's see, so we have a computer running several programs at once. These are my simple examples. We have a web browser, an instant messaging client, which is now in the browser, an email client, which is also in the web browser. Okay, so let's assume that we have 4 different programs, and we're all doing these 4 different things, and if you look at them, you say, hey, guess what? All of these things are going to have periods of time where they're just waiting. Web browser, okay, come on, click a link so I can do something. IM client, somebody send a message to this person so that I can do something, and so forth. Okay? None of these programs completely consume the processor. So let's say that each program's context, we have a way of capturing it, and we have enough memory. You'll notice here we have tons of memory so that we can store each program's context. We have a way of plopping each program's context into some range of memory. Okay, this is not the same as what we did before. This is a little bit more clever. It's only slightly more clever, which is what's cool about it, is that we can take a little baby step and be more cool. So text editor, IM client, web browser, email client. Now we also have this special region of memory that can be used by the currently running program. In this case, the text editor. Okay? And the constraint is that the text editor can only see the information that's inside of this special region of memory, which I call the box. So it can only see stuff inside the box, and anything outside of the box, it can't see. But while it's running, it has exclusive access, sole exclusive access to the CPU. It doesn't have to worry about what other programs do with that memory region, because it's that program's memory region right now. It doesn't care what other programs would do with the processor, the registers, and so forth. It doesn't care, because it has sole access to the processor. Now what happens is, again, we'll use our magic wand right now, but somehow we suspend this program. Either it says, hey, I'm done running for a while. The user is waiting for, more inspiration to type that hum paper or whatever. And so it goes ahead and says, hey, I'm ready to get off the processor. And so it gets suspended, and we copy the program out of the box back to its memory area where its context is stored. And recall, of course, this includes the registers from the processor. This includes the stack pointer, the instruction pointer, the flags. All of that stuff gets copied into the context for the text editor now. And then we pick some other program that should run, and we copy its context back into the box. And we set the registers back to what the IM client's registers were when it was last suspended. And we set its stack pointer and instruction pointer and flags register and all of that stuff. We store it back down, and then once we've done that, then it can start running. And as far as that program knows, it never stopped running because something interrupted it, and then it didn't know that it got copied away and that somebody else got the processor for a little bit. And then when it gets copied back and starts running again, it picks up exactly where it left off. And so it just continues running. If it were to look at the time, it would notice a little gap, where it suffered amnesia, like this time passed and I wasn't doing anything. But that's all that it would really be able to notice. Okay? Does that make sense? Yes?
So how does this fix if the memory grows? Like we need more data inserted?
We haven't solved all the memory issues right now. There is a really obvious cost as well, which is copying the entire context. But let's say that we gave each program 1 gig of space. Well, then we could have that box be 1 gig, and then we'd need n gigabytes of memory for each process we want to be able to run concurrently. So you can see that we clearly have some memory issues that we haven't solved yet. So far, all we've really done is virtualize the processor. Okay? I want everybody to make sure you understand it. There's other issues as well. If I didn't just say this, I'm going to be embarrassed if I did. Copying that information back and forth is expensive too. Copying the context into the box, copying the context out of the box. If a program's actually using a gig of data, that's a gig to copy. That takes time. This was a problem that affected computer systems and operating systems back in the 50s and the 60s when they were building these things for commercial use. So yeah, we haven't solved any real memory problems yet, just to be very clear. We're only solving the processor virtualization problem. Okay, any other questions? Okay, last thing to mention, of course, is that you have a physical control flow and a logical control flow. And you can see that with this whole processor virtualization thing, we have a physical control flow that hops back and forth between various programs. So the email client runs for a little bit of time, and then we hop over to the IM client, and it runs for a little bit of time. And then we hop over to the text editor, and it runs for a little bit of time. And so we're hopping back and forth. That is the physical control flow. This is what the operating system is doing for you behind the scenes. It's doing a lot of other stuff. The stuff between the two lines here, switching back and forth, that's magic is happening here. We're going to start talking about what goes on there. But within each process, because we're always very careful to save the context when the process has to get off the processor, and we're careful to restore the context exactly as it was when we get back on the processor, as far as each program knows, it is just logically executing through that program without any interruptions, without any jumps. It just is executing as if it had sole access to the processor. So we call that the logical control flow through the process. Okay, does that make sense? Let's see, so yeah, concurrent processes. And this is another really important thing. Do concurrent and parallel mean the same thing? Yes, no? Parallel means I'm doing multiple things at the same time. I can only have parallel execution if I have multiple cores. Concurrent execution is different. It means that I have overlapping logical control flows. Okay? So you can have concurrent execution on a single core system. You cannot have parallel execution. You can only have parallel execution if you have multiple cores that are able to process things at the same time. Make sure you understand that, not so much because it matters in CS24, but it matters in life as a software engineer, because if you don't understand the difference between those two concepts, you'll kind of look dumb if you don't use them correctly. Parallel, I'm doing multiple things at the same time. Concurrent just means I have overlapping logical control flows. That also becomes extremely important in operating system implementation. Okay, so that is an idea of how we can actually virtualize the processor. There's a number of issues that we haven't solved yet. Who manages all the processes? We haven't talked about that because we sort of have this thing that programs can only see stuff inside the box. So, well, what's outside the box? They can see everything that's inside and outside the box. Okay, so we'll talk about that. How do we ensure that processes can't see each other, but the manager can see everything? We'll start talking about that. But really, the issue with memory is that we aren't going to talk about the solutions for memory management until we get into virtualization of memory. So just keep that on the back burner in your minds, but we'll get to it in a week or so. And then, of course, how do we actually interrupt a program? Because we haven't talked about how do we actually preempt a process that has sole access to the hardware. How do we do that? How do we actually interrupt that program while it's running? So we will go ahead and pick those things up next time.